All right, now we're going to do the calculus parts of E&M. So this is everything that's not circuits, but involves calculus. So we're going to do E fields, we're going to do charge distributions, Gauss's law, Biot Savart, Ampere, Faraday, all that stuff. So this is where a lot of the tricky concepts are, is sort of in this section. All right, so first we're going to relate E and V via calculus. So what do we do if we're given a potential function v of x? How do we find the field? Well, we said that E field points downhill in the electric potential. So we can say that E points downhill is sort of how we interpret this. And then if you have to go the other way, where if we know that E is the slope of V, that means that V, that if we sort of add up all of our E field, that's going to tell us the total change in V. So instead, we could rearrange this relationship to say delta V is equal to the negative of the integral of E dr, or sort of any direction. So how do we interpret this? Well, this says sort of the same thing, but this says moving along E results in a decrease in potential. Because if E is the downhill slope of V, if I'm traveling with the downhill slope, I must be traveling downhill. All right, now let's do an example. Now we have this function V. What's the electric field? Well, the electric field is just going to be the derivative with respect to x of our V expression. So this would just be negative 2ax plus b, taking the derivative of our potential function. Where is the electric force acting on a charged particle equal to 0? Well, we know that F is equal to QE. So if the net force on a particle is 0 due to the electric field, this tells us that E is 0. So all we want to do is find that position. So we just set our expression from earlier for the E field equal to 0. And oh look, that's a value that should seem familiar to any algebra students. Negative b over 2a. Why is that significant? Well, this is the parabola equation for the potential. And the force is 0 apparently at the vertex. Yeah, that should make sense, right? Because the vertex is the only spot with 0 slope. So there's no push uphill or downhill. That is the hill. Now we'll go the other way. The vertical component of the E field is given by this expression. Calculate the potential difference moving from 0 to 2. Well, delta V is just the negative of the integral of the E field in a certain direction. So we go from 0 to 2. Our function is 6y squared. So we get the negative of 2y cubed going from 0 to 2. So we get 2 times 2 cubed, which is 16, with a negative in front minus 0. So negative 16 volts. Which position is at higher potential, 0 or 2? Well, we just got a negative answer from moving to 0 to 2. So this means V of 0 is higher than V of 2. Justify using our calculated potential difference. Well, delta V from 0 to 2 is negative. So this means potential decreases from y equals 0 to y equals 2. Justify by referencing the direction of the electric field. Well, if we think about what this looks like on a graph, it says the y component of the E field is positive 6y squared j hat. So that would be like there's no push right here at the origin, then there's a small upward push, then there's a bigger upwards push, and a bigger upwards push, and even bigger upwards push. And remember, we said that E field points downhill. So since E points downhill, we're traveling along E, and E points towards lower potentials. So that's about all you can do with field and potential. So if you have the potential, you take a derivative to get E. If you have E, you integrate over an interval to get delta V. And of course, there's those negative signs. All right, now for our first big topic, continuous charge distributions. What is the potential of a charge distribution? Well, V for a point charge is kq over r. So if you have many, many kq over r's to add up, V becomes k times the integral of dq over r. And then for E field, the E field of a point charge is kq over r squared. So E of many of those is k times dq over r squared, but we get an r hat to remind ourselves of the fact that E is a vector. So all we're doing is just replacing the summation with an integral. So potential is a scalar, E field is a vector. But also, don't feel like you have to integrate to get E. So the reason we do V in a lot of cases is some people really hate the vector stuff. So you can also just find V first without using vectors and say E is just the derivative of V downhill. And you can use that to avoid vectors. So some people actually like to just find V first, then take a derivative, because they don't want to do the component thing for some of these. Now, related to charge distributions would be charge density. So we have linear charge density lambda, which is charge per length. We have area charge density, which is charge per area. And we have volume charge density, which is charge per volume. So our common substitutions here is, well, you can get Q. You can get a tiny chunk of charge dq by doing lambda times d length. That's just a definition. And the only special kind of length we have is along a circle. Length would be arc length, r d theta. Most of the time, you're just doing this differential directly. Now, dq, in general, is sigma dA. I don't really see a scenario where you'd be asked this in E&M, but the only kind of symmetry that you'd have to deal with would be like a charge disk, although that's actually outside the scope of APC E&M, where the small area element of a disk would be the ring 2 pi r times its thickness dr. Then for volume, a tiny amount of charge in a volume would be charge per volume times volume. And this is our volume element for a sphere. It's just the sphere area times the thickness. Or if you have a cylinder, the volume element for a cylinder would be 2 pi r L dr for a cylinder. So that would be if you're integrating to find enclosed charge in a sphere or cylinder, you have to replace this dV with a relevant volume formula. So you find the volume formula, for example, like 4/3 pi r cubed, and then you take the derivative of this with respect to r. So that's how you know like what to plug in for dV. You find a v and take a derivative of it. Here are your charge distributions to know for E&M. So we have arc, ring, collinear line, bisector of line. So for the arc, this is a linear charge density. So we say dq is just lambda times d length. But this is an arc, so we have to replace d length with r d theta. Now for our potential, we just integrate. V is the integral of k dq over r. But all of the arc is a distance r away. So actually everything factors out. And this just looks like a point charge, kq over r. Now you might have to determine q in terms of lambda. It'd be lambda times pi r for a half circumference. And then the setup for electric field, we have to determine if we need vectors or not, because E is the integral of k dq over r squared r hat. So if I look at the arc, I would get pushed away from this segment, and I would also get pushed away from this segment, and we see that there's some symmetry here canceling horizontally, so we just get a net field that's directly vertical. So we'd set this one up by doing k times the integral of dq, which we said was like lambda times r d theta for dq, divided by r squared, and then we have to tack on that sine theta to extract the vertical component. And you integrate from like 0 to pi, or 0 to, or pi over 2 to negative pi over 2, depending on how this arc is oriented. Now for the ring is special because everything factors out. So actually there's no dq substitution needed for the ring. So if we try this once again, you'd get v is k times the integral of dq over r. But notice that every single segment on the ring is going to be a distance of this blue line apart. And this blue line, we're usually looking a distance, I'll call it z, kind of above the axis point here. So this distance would just be the Pythagorean distance, z squared plus r squared. And this just ends up being equal to kq over square root z squared plus r squared. Because it looks like a point charge, because all the charge is this blue radius away. If you sweep this radius all the way around the ring, the distance does not change, so it's just kq over r. But then if we look at what's going on again with the field, we see once again, everything cancels except for these vertical components. So we do the same setup as before, where E would be equal to k times the integral of dq over r squared times sine theta. And what you'll actually get is you'll get the 3/2 power thing happen here, because everything is constant in this integral. So you get kq over r squared times sine theta. So you get kq over the Pythagorean distance times sine theta, or we usually define that polar angle as z over r. So you get that 3/2 power when you simplify. Line, collinear with one end. So here this is a line charge, so dq would be lambda dx. Nothing to do there. Then for your v is just the integral of k dq over r. So this is just k times the integral of lambda dx over x from a to a plus l, because you're a distance a from one end, and then the farthest rod segment would be a plus l. So you get a natural log term in there. And then for e, you do k times the integral of dq over r squared, and you don't need an r hat because all the components are going to just push to the right. So there's no extraction needed there. So this looks the exact same, except we just have a squared denominator. Now this is one where it might be easier just to do v, take a derivative to get e, just like up here. You could take a z derivative to get this expression. This is really the chain rule, right? Then for the bisector, you only have to set this one up. So the difference for the bisector is if we look at different points along here, once again, we see that we're going to get another trig factor. If your pictures look like this, it'll be sine, but if they're rotated, it of course can be cosine. So once again, dq is just going to be lambda dx. V is kq over r with no square. R is the Pythagorean distance, and I go from half of the rod length one way to half of the rod length the other way. So the limits are actually the weirdest part for setting up the bisector one here. Then for the E field is k times the integral of dq over r squared r hat. dq is still lambda dx. R squared would be the square of that Pythagorean distance. And we multiply by sine theta once again. So we'd get k times the integral from negative L over 2 to L over 2 of lambda dx over x squared plus a squared times sine theta, which is a divided by the quantity x squared plus a squared under square root. So these are the derivations to kind of know. These are entirely the scope of E&M with charge distributions. You need to know how to set these up, probably do them. Nothing more than this, though. All right, flux. What is flux? Flux is the electric field piercing an area, or it's the sum of all of the E's piercing an area. This is the flow into / out of a closed surface. It's just the amount of field that penetrates a 2D loop, though. What's the general expression for calculating electric flux? Well, the general expression is this one. We have to integrate E perp times dA. But the most common simplification is that you can just, for a constant E field, take the perpendicular component, multiply that by the area. Like, for example, in this one, we see that this component of the E field is not piercing the loop, but this component of the E field is. So this is my E perp. It says our E field is E. So our E perp here is going to be E times sine 30 degrees, because sine is opposite. So my flux is just going to be E sine 30, which is the perpendicular component, times A, or since sine 30 is 1/2, this is just 1/2 EA. Now it also works in 3D, where I have a sphere of radius r centered around a point charge q. So once again, I can just use the fact that this is perpendicular everywhere. So flux is just equal to E perp times A, which is actually just EA in this problem. And then what is E? Well, this is from a point charge. So E from a point charge is KQ over R squared. And area of a sphere is 4 pi R squared. So we get 4 pi KQ. And actually, you get a much better, or much more familiar answer if we replace K with 1 over 4 pi epsilon naught. And we see we get Q divided by epsilon naught, which is Gauss's law, which says for any closed surface, this should be the flux through it. Now you can also have to integrate. So here we have a rectangular loop. There's an E field out of the page with increasing magnitude. So something like this, where we're getting more and more E field. So this is why we have to break it into strips. So anytime you have a case that looks like this, we're splitting this probably into rectangles, where it's going to have some length, in this case L, its width is dx. And now we can set up our integral, because flux is the integral of E perp dA. Our closest strip is at x equals 0, and our farthest strip is at x equals 2L. Our expression for E field was A times x, and dA we said was L times dx. So A and L are both constants. So now if we just evaluate this integral here, we'd get AL times x squared over 2 from 0 to 2L. So we'd get 4L squared over 2, which is 2L squared. So 2AL cubed, it looks like, will be our flux. So again, just be able to make that area substitution. Most people know it's an integral, but you might forget how to set up this dA for the rectangle. So break it up into strips and do the length and width. One of them will be like a side length. The other one will be a dx or dy or something like that. All right, now it's time for Gauss's law. What does Gauss's law state? Gauss's law says the net electric flux through a surface is Q enclosed over epsilon naught, which means the only thing that affects electric flux is Q enclosed, nothing else for a 3D surface. So if we place a point charge at the center of a cube, for example, It's important for the setup that this is the center of the cube. What's the flux of the entire cube? I don't care what the surface is. I just use Gauss's law. The net flux of their surface is just Q over epsilon naught. I can just stop. It's not like E times A, where A is like the 6 of these, because E is not constant. It would be a mess trying to do this by hand. It actually works. If you're like proficient in Calc 3, this might be an exercise you find interesting, but it's kind of awful. What's the flux through one of the faces? So this one looks really awful because I'd have to integrate E perp dA on like one of these faces. But also we can just use symmetry because it's Gauss's law. So we know that flux, due to symmetry, it has to be the same through all these 6 faces because we're at the center. So phi through one face must just be 1/6 times the total flux, which is 1/6 Q over epsilon naught. What's the net flux through the cube if the side length of the cube is doubled? This is the same because Q enclosed is the same. That's a common trick question. If we change the Gaussian surface side length, we are not changing Q enclosed if it's already fully trapped. So it's going to not change the flux because flux increases with area or r squared, and field decreases with area or r squared. So those two effects exactly cancel each other. So flux does not depend on the surface you pick. It only depends on how much charge is enclosed. Now we're going to talk about the conductor sandwich, also known as the surface charge theorem. So what is the net charge on the inner surface? So all of these metals, anytime you see a metal, we know that E equals 0 and V equals a constant. We want the net charge on each of these surfaces using Gauss's law. So using Gauss's law, I know that the E is everywhere 0 inside this conductor. So I know that the flux inside the conductor, a surface inside the conductor, would be EA, where E is 0 everywhere. So I know the net flux actually has to be 0. So what this means is that the net flux, which is equal to Q enclosed over epsilon naught, is equal to 0. So what this means is that the net enclosed charge has to equal 0. So where's that charge going to live? Well, there's charge in the cavity, and there's charge on this sort of surface. So if I draw myself a Gaussian surface, the only place where charges can live that aren't the cavity is this inner wall of the conductor. So actually what we know here is that there must be exactly negative Q distributed along this inner surface to cancel the cavity. So this is the first part of the surface charge theorem. The inner wall of a cavity cancels whatever net charge it's staring at. So this cavity stares at a Q, so it's going to have a negative Q induced to cancel. So Q inner equals negative Q. The inner cavity always cancels. Then, what about the outer charge, outer surface charge? Well, here's where you use conservation of charge / the shell theorem. So we said this entire system has Q and lowercase q. So if I go far, far, far away, or just anywhere outside really, it should look like a system who I shrink down to Q and little q. So outside, it looks like this, where I shrink it down to a dot, and it holds the net charge of the system. So as a result, that must mean the outer surface holds the net charge of the system. So this means Q outer is the net charge of the system, which is just denoted as this. So those are the two parts of the surface charge theorem. So the first part of the surface charge theorem says the inner surface always cancels what it's staring at, and the outer surface just holds the net charge of the system. So before I started counting charges, I could have actually worked backwards too. I could have said I have Q here, I have Q here, so all of those go to the outside surface. to make it look like a shell theorem example that works. Now you could also like do a accounting thing where like you have big Q to give away between the two surfaces, and if I give minus Q to the inner surface, I must have Q minus minus Q to give away to the outer surface, and that works as well. Let's just do an example from context. All right, inner surface. So we want the charge on each of these surfaces here. This is a pretty classic conductor sandwich. So for the inner surface, we always cancel what we're staring at. So this has 3Q to give away. So I know the two surfaces have to add up to 3. So first, negative Q to cancel what I'm staring at. Then for the outer surface, it holds the net charge of the system. There's a Q and there's a 3Q. So that's going to be 4Q. You could have also figured that out by charge conservation. Find the flux through each of these surfaces. Well, if I'm at 0.5 R, 0.5 R is this. So I'm just enclosing. So for finding the net flux, we're just going to use flux equals Q enclosed over epsilon naught. Well, if I'm half R, that means I'm somewhere in the cavity. So the only thing I'm surrounding is Q. So this would be Q over epsilon naught. If I'm 1.5 R's in, I'm here. So I'm surrounding the Q in the cavity and the minus Q on the inner surface. So that's actually 0. Because I'm enclosing canceling charges. And if I'm all the way outside, I'd be enclosing Q, negative Q, 3, and 4. Or sorry, not 3. Because we distributed the 3. I'd be enclosing Q, negative Q, and 4Q, which makes 4Q overall. Because these two are going to cancel, and then we got that. Sorry, I had a moment there. You're just looking at what's the net charge enclosed. So if I'm in this region, I'm only enclosing the Q. If I'm in this region, because this 3Q does not exist. This 3Q does not exist because charges on a conductor go to the surface. So that 3Q is not real. That 3Q is really just these two charges. So that's a good strategy as well, is cross off that once you've figured out how it distributes. So Q and minus Q, which is 0, and Q minus Q and plus 4, which is plus 4. What's the field in each of these regions? Well, this is a sphere, so just use shell theorem. So this is KQ over R squared in the cavity. It's 0 in the conductor. And then it's KQ over R squared outside, except the Q enclosed is 4. All right, it's just various shell theorem applications. Oh, let's sketch some graphs. Electric field magnitude. So we know that it's going to explode to infinity when we're in the cavity, because we're right on top of a point charge. Decrease, 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 decrease. Then we quickly jump to 0 inside the metal. And then we jump back up into K again. Then for our potential is easiest to go backwards. So this is positive charges, so we know it's going to be hills, so positive only. So we know it's going to decay to 0. My potential increases as I get towards the sphere. Then I reach a metal region, and we said V is constant in a conductor. Sorry. This is why we don't graph live. Something like that, where we get 1 over R outside, looks like a point charge, it's constant in the metal, and then it's 1 over R once again, and it explodes to infinity. Because potential is like your height, or we say E points downhill. So if E is always pointing this way, we know that the sphere must be at higher and higher potential as we go. So again, we know E equals 0, V equals a non-zero constant. All right. Now let's do the meat of Gauss's law. where we want to actually find E fields with it. So when is Gauss's law useful? Well, we only use Gauss's law usefully for finding fields when there is symmetry. So we use Gauss's law when there's spherical, cylindrical, or planar symmetry. So spherical, if your charge distribution is a sphere, cylindrical, if your charge distribution is a cylinder, or planar, if your charge distribution is a plane, because if you draw your field lines, your field perfectly pierces the surface perpendicular at all points, depending on what you draw here. So for the plane, you actually draw like a cylinder like this. So let's make sure we can do these. So for a point charge, the easy part of Gauss's law is the flux. So flux can be found by doing E times A in cases of symmetry. So for a sphere, we're a point charge, we're drawing a sphere, and the flux is E times area of a sphere, 4 pi r squared. What's the enclosed charge? Super easy. You just count. It's Q. So what's the field plot from that? Well, it's a point charge, KQ over R squared. So 1 over R squared. What about a line charge? Hello? Okay, guess I erased that. Whatever. So for a line charge, we get a very long line charge at least. We get a field that looks like this. So for a Gaussian surface, we draw a cylinder like this that's perfectly pierced, and it is going to enclose some charge, depending on the length that you enclose. So the flux is going to be found through a barrel of a cylinder, where we multiply E by the area of a cylinder, which is 2 pi r, times this fake distance L, or I like to use X for made up distances. And it'll eventually cancel out because that is also in your expression for Q enclosed. Because for your enclosed charge is just lambda times X. Charge per length times length. And we see there's X's on both sides of Gauss's law, and it ends up working out. So there's actually one less R in this problem, so it's still like a decreasing E field. It's just 1 over R, not 1 over R squared. Now for the plane of charge, we draw this sort of Gaussian pillbox where our flux, it's once again a cylinder. It's just oriented the other way, where we have an E field piercing 2 areas worth or 2 caps worth of area. And then the enclosed charge would be the charge per unit area sigma times the area enclosed in the plane, which is A. So once again, this fake area, A, that we just made up will cancel. And there's no dependencies here at all. So actually, E from a plate is constant. So be wary of that. So if you double the distance from the plane, if it's a large plane, you will not feel a different E field. Now, if we have a sphere with uniform density, it's still a sphere. So we still do E times 4 pi r squared as our flux. But our enclosed charge is going to be rho times V enclosed, which would be rho times 4/3 pi little r cubed. Or if you actually have the total charge in your sphere, you could write the density as Q divided by 4/3 pi big R cubed, and then multiply that by the enclosed volume, and you get this interesting like cubic fraction ratio. So you see you're going to get 3 R's on the Q enclosed side, but only 2 on the flux side. So as a result, we actually get a linear E field inside until you reach the surface, and then it's just shell theorem, KQ over R squared. Now the only difference if there's variable density in addition to me, I guess why not? I guess I'll just do this. We want to find the enclosed charge in here. So this is not a uniform density, it's a density rho of r. So it's still a sphere. We're still using a sphere, right? The flux is still going to be E times sphere area. But here, the Q enclosed is actually the integral of rho dV. And for a sphere, dV is 4 pi r squared dr. So your Gauss's law life hack is that the differential in your integral, if you need it, is always the same as your Gaussian surface area factor. And now if you do this, you'll get usually a concave up E field inside. So I don't know what that's proportional to, but it depends on the power. It's actually one more than the power in the density function. But it's still that same idea where this is like kq over sphere radius squared. So if you had a linear function for rho of r, you'd have a quadratic E field. Now for the slab, do I think the slab will show up? No. The slab is like the thick cousin of the plate. So here we have, once again, we're using a plane, or sorry, a cylinder, where we have an E field piercing 2 areas worth of area. And our enclosed charge will be rho times the volume, which would be rho times area times thickness. So once again, this fake area will cancel, because volume is area times thickness. And if you do the slab, you'll see the slab has an increasing E field, and then it levels out and becomes constant because we said it looks like the plane from outside. So this will be linear and this will be constant. So that's everything with Gauss. Now we have Biot Savart, which will not show up. Please memorize this loop formula and then you never have to do Biot Savart. I can't guarantee that, but I could pretty much guarantee that. Biot Savart is not going to be an important part of the test. So Biot Savart says the magnetic field is equal to mu naught I over 4 pi times the integral of dl sine theta over r squared. How do we define the angle theta? Theta is between the wire and observation point. So you have to make sure it's the angle between the wire and your observation point. Using the Biot Savart law, this is the only case you need to really be familiar with. Like the wire case exists as well. Yeah, I did include it. But memorize this loop formula. So magnetic field is equal to mu naught I over 4 pi times the integral of dl sine theta over r squared. All right, so we have a loop, and this would be our current segment. So we see that since it's a circle, that was definitely a right angle. So I can just get mu naught I over 4 pi integral. What is dl? I got dl times sine of 90 degrees. Radius of the loop is r. All of those are constants, so I just get mu naught I over 4 pi times the integral of, or sorry, r squared comes out too, of the integral of dl. So what would be the dl of the loop? Well, if I add up all the little length segments of the loop, I get the whole loop. How long is a loop? Well, a loop is a circle, so I just use the circumference, 2 pi r. And notice we get almost b wire. We get mu naught I over not 2 pi r, but 2r. So that is the case you need to know. You need to just, I would say, just know that loop formula. It's almost b wire. So sometimes you'll see like cousins of the loop where it's like semicircles, where we have this situation, for example. So here we have b net is going to be equal to b inner plus b outer as vectors, of course. So we know that b from a semicircle should actually just be 1/2 of b from a loop. So it's just 1/2 times mu naught I over 2r. So for our inner loop, it has radius r. And if we do our right-hand rule, we see it's going to curl into the page. Or sorry, it's going to curl out of the page on this side. So this wire actually generates an out of the page field at this point, because counterclockwise is positive. Then over here, Since it's the opposite orientation, this is going to be into the page. So we get 1/2 times mu naught I over 2r out of the page plus 1/2 times mu naught I over 2 times 2r into the page. So now we got to do some subtracting. So we get mu naught I over 4r out plus mu naught I over 8r in. And oh boy, what is that? 1/4 minus 1/8. 1/4 minus 1/8. That's just 1/8, isn't it? Because 1/4 is 2/8. Yeah. So we get mu naught I over 8r out because the closer wire generates the larger field. We'll scoot it over because I got cut off. So again, all I did is I halved B loop to get B from a semicircle. And these segments don't do anything because they're parallel to the observation point. All right, now last thing you might have to do is you might have to do the setup for the integral for B from a wire that's finite. In the infinite case, we know it's going to be mu naught I over 2 pi r. So we can just define our usual triangle here, where this is some distance x, this is a right angle, this is x squared plus a squared, all under square root. Now we have to be careful about how theta is defined. Theta is between the current segment and the observation point. This is the observation point vector. This is the current segment, so I must pick the angle between those two rays, which is this. So I can say that B is equal to mu naught I over 4 pi times the integral of dl sine theta over r squared. X can be half of the wire in one direction or half the wire in the other. R squared is just the square of the hypotenuse. And what is sine theta? Sine theta is opposite side over hypotenuse side. So we get the 3/2 again. I should make this an x. Ugly, ugly, ugly. Now, if you evaluate this in the case that L goes to infinity, you do actually get mu naught I over 2 pi r. So for any trig sub enjoyers, you can verify that if you don't believe me. So just like electric fields by hand with integrals were annoying, so are B field integrals. So we have better ways, and if there's symmetry, there's Ampere's law. Ampere's law says the magnetic circulation, B parallel dl, is equal to mu naught I. So what does this say? This is not flux. This is something called circulation. So what does this mean? Magnetic fields circulate around currents. So what's the value of this integral? Well, just like flux only depends on enclosed charge, circulation only depends on enclosed currents. So we know that the magnetic circulation B parallel dl is just mu naught I enclosed. So what is the I enclosed? Well, I have a 5I out of the page, I have a 1I out of the page, and I have a 2I into the page. So I subtract the 2I because I said that's into the page. Sign doesn't really matter with these as long as you add like currents and subtract opposite ones. 6 and 2 is 4, so this is 4 mu naught I. When is Ampere's law useful? Ampere's law is useful when there is symmetry, just like Gauss. So for Ampere, there's really only two cases. We'll just pre-fire my solenoid here. All right, so magnetic fields circulate around wires. So if you have something like this, you have circular symmetry. And for a solenoid, this is actually a uniform field. Sorry, I had to think about which way it goes. So we actually draw this sort of like magical rectangle. The solenoid one is odd. Please review the solenoid one on the next page. So if we have a wire with current, this is like the case of Ampere's law. What is the circulation? Well, we use a circle. There's a B field B circulating around the entire perimeter of the circle, 2 pi r. Enclosed current is just I. So we get our just classic wire result, mu naught I over 2 pi r. Now, what if we're inside a wire with uniform density? Well, we're still using a circle because there's still circular symmetry. So it's B times 2 pi r. What is the enclosed current now? Well, enclosed current can also be thought of as J times area enclosed, because that's what current density is. It's J. So J times the pi r squared enclosed by my loop. And you might write J as the total current divided by the total area. So you get not a volume fraction ratio, but an area fraction. And if it's uniform density, once again, uniform density means linear inside. And there's the sort of shelf theorem for wires that says any wire looks like mu naught I over 2 pi r outside. Now, if there's a variable density, copy pasting is not my friend today, apparently. You know, that would have taken way less time just to draw that. We're still using a circle, which is B times 2 pi r. But here, current is the integral of J dA, which is equal to the integral of J of R times dA, which is 2 pi r dr. And just like for Gauss's law, we said our Gauss's law hack is that our volume differential was always the same as our flux factor. Same idea with Ampere's law. The thing that goes on the left side of Ampere's law, the circulation path, is the same as this like differential. So if there's variable density, you're usually going to have like a concave up before your mu naught I over 2 pi r. Then for the solenoid, please tell me the solenoid stayed. Good enough. So for the solenoid, this is where we actually use a rectangle, because a rectangle travels nicely tangent to the B field. Rectange. So the circulation here would be there's a B field circulating only for a distance x. It only circulates on this side, because outside the B field is negligible, and on these paths we're traveling perpendicular. So it's actually just B times x. So what is the enclosed current? Well, the enclosed current would be the number of enclosed coils. We'll call it enclosed. It's going to be the enclosed coils times the current, because each coil carries a current I. So how many coils did I enclose? Well, there's n coils per unit length, which is also called lowercase n. And I'm going for a distance x. And then I have I. So solenoid is kind of tricky for the setup. Now, the solenoid, we also assume it's sort of the magnetic version of the capacitor, where it just traps a constant B field inside. Edge effects are negligible. Freaking conducting slab. I hate the conducting slab. If the conducting slab shows up, College Board hates you. For the conducting slab, this is just like a cousin of the solenoid, where it's still going to be a rectangle. We go B times x again. So the enclosed current is just going to be J times area enclosed, which would be J times the area enclosed by this shape, which would be some fake distance x you make up by some like height z. You can review my section on Ampere's law if you want for this, where we go in actual detail about it, but it looks a lot like the insulating slab for Gauss. All right. Home stretch, Faraday's law. What does Faraday's law state? The induced EMF in a loop is equal to the rate of flux change. How do you induce an EMF? You change the B field. Flux is that, right? You change the B field. You change the area, or you change the angle. or which is how much of the B is perpendicular. So you could have a loop, and you could say initially the B field is this, and then I increase the B field to this. You could change the area. How do you change the area? It is like only this, by the way. It's the bar on rails problem. That is a very thick bar. Moving bar, right? You're effectively increasing the area of this loop. And then changing angle, this is only ever rotating a loop in a magnetic field. So like this would be something like this where you rotate the loop. So sometimes it's perpendicular to the field, sometimes it's parallel, changing the angle. But I thought flux was zero. Gauss's law says flux is zero for magnetic fields. Nope, only closed surfaces. So phi b equals 0 for 3D shapes. Loops are 2D, so it's fine. What is Lenz's law? Well, Lenz's law says that there's an induced EMF, so there's an induced current. What do we know about that current? Lenz's law says induced current generates a magnetic field that opposes the flux change. So for example, in the first example, you're getting out of the page, out of the page, out of the page, more, more, more. So you need to generate a B field that does this, which would be clockwise. In the bar on rails, you're getting more out of the page, more out of the page, more out of the page. So I would need into the page B field. So the first variant of Faraday's law is the just derivative approach. So the magnetic flux through a loop varies according to this expression. Derive an expression for each of the following. What's the EMF induced? What's the current induced? Power, energy. All right, well, EMF induced is just d flux dt. So I'm literally just taking the derivative of b times t, which is just b. What's the current? Don't forget Ohm's law exists. Just divide your EMF by current or resistance and you got current. What's the power dissipated? Pick your favorite. Usually for Faraday, you want EMF squared over resistance is the easiest one. Notice this is obviously I delta V because I was B over R and delta V was B. What's the total energy dissipated? Energy is equal to all of the power dissipations times time. So the power was B squared over R times dt, and we go from 0 to capital T. None of this is actually changing. So we just get energy as power times time in this scenario. Now we have just like a direct flux change. This is a problem you definitely need to know how to do. So this is the magnetic equivalent of like making your flux strips. So this magnetic field would be out of or into the page. And it decreases as we go to the right because we're getting farther from this wire. So we'd get something like this. So first we want to just find the flux through this loop. So I can't just do B times A because the B field is changing because this is a wire. So that B is decreasing according to mu naught I over 2 pi x. So instead, I have to just integrate flux like I did with the E field. So I'm going to break it into strips like this. This would be dx. This side length is s. B from a wire is mu naught I over 2 pi x. dA, the area of this strip, it has height s and width dx. The closest part of the loop is s away. The farthest part of the loop is s and another s away. S and s makes 2s. Lots of stuff factors out. And we get an extra special integral because this is 1 over x. So this would be ln. So this would be ln of 2s minus ln of s. Or, using the subtract equals division rule, mu naught is over 2 pi natural log 2. Suppose we vary the current. What is the EMF induced in the loop? Well, EMF is just going to be d flux dt, which would be the derivative with respect to t of I is c times t, so I'm just going to replace my I with ct. Whole lot of scary looking stuff just for it to be a bunch of constants. Only thing that matters is that c times t gets hit by the derivative, so that's just c. So this is also a constant EMF because the current is decreasing at a constant rate. What is the direction of the induced current within the loop? Well, if the current, it says it's increasing, right? Yeah, the current is increasing. So I'm getting more x's, more x's, more x's. So what does that mean? Well, to oppose more into the page B field, we need to get out of the page B field. So that's going to be counterclockwise. What's the direction of the net force on the loop? Well, here's how you do it with Bill forces, where we said it's counterclockwise, the forces, or sorry, the current. So if we did our Bill forces, we would get a repulsive force between those wires, because opposites repel for wires, and then an attractive force over here, but the attractive force would be smaller from the light currents because the light currents are farther apart. So it is to the right because opposite currents repel. And in this problem, opposite currents are closer together in this scenario. There's also some other things you could do to justify this, like saying, well, this loop is very unhappy that the wire is increasing the current to change the flux. So since this loop is not happy that its flux is being increased, the loop is going to try to get as far away from that increase in current as possible. Last one. Conducting bar is on rails, blah, 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 all the usual stuff. It's late. All right, what's the direction of the current in the bar? A couple ways of doing it. Hall effect says if I QV cross B, the positive charges would get bunched down here. Meaning I essentially have this scenario. So that would generate a clockwise current because my positive end of the battery is down. Hall effect says clockwise. Lenz's law says I'm getting More circles, more circles, more circles, more circles. We don't want that. So Lenz's law is going to say we generate x's, which is clockwise to oppose the change. Lenz's law is easier to explain. Flux is out of the page and increasing clockwise current to oppose flux change. This is how you structure a Lenz's law derivation. Say the flux is increasing, state the flux change is being opposed, and put it all together. Now we have to make this a Diff EQ. So starting from Newton's second law, do a Diff EQ. Well, Diff EQ in this class, it's either Kirchhoff loop rule or it's F equals ma. In this case, it's F equals ma. With acceleration being the derivative of velocity. So what is the net force acting on this bar? Well, there will always be, in every bar rails problem, a resistive bill force. The magnetic force always resists motion due to Lenz's law. There's always a bill force resisting your motion. So F net is help minus hurt. Anything helping the bar? No. What's hurting the bar? Bill. This is motional EMF. Anytime you have a bar on rails, we can use the motional EMF equation, and then you can use Ohm's law to get the currents. You just divide by R. So that gets us our expression for net force. And then we can solve and we get dv dt equals negative b squared L squared over mr times t. Nope, times v. So that's why we say this is a drag force, because it's proportional to your velocity. By solving your differential equation, derive an expression for v as a function of time. Okay. Well, we have dv dt equals negative b squared L squared over mr times v. So I can send the dt over to one side. But I also need to separate and get the v on its own side. So I can divide by v. So I get dv over v equals negative b squared L squared over mr times dt. Now we integrate. Time goes from 0 to t. V, I was launched at v0, and I end at some speed v I want to find. This is just a natural log integral. And the right-hand side is just this whole thing times t. So we exponentiate both sides, multiply by v0, and we get an exponential decay. V equals v0 e to the negative b squared L squared over mr times t. Lovely. Now also be aware that other versions of this exist where like your help force could be mg if it's a vertical bar, or it could be mg sine theta if it's a ramp where only part of gravity is helping you go down. So just be aware of that. This is definitely totally exam material. I don't know what year they're going to bring back the differential equation for the moving bar, but I feel like we're due. I actually really like the moving bar question. Sorry, that was just a really brutal hour of calculus nonstop. This is where maybe 3 of the 4 FRQs could come from on any given year. Like, this is the most deep part of the content. And then we just pick up with some circuit stuff to end it.